Welcome everyone to week 2 of Essential Maths. We're going to jump straight into it. So we are going to we are describing the associations between variables of bivariate data. So the idea is to understand what is a variable, what is bivariate data, and what are the relationships that we can get with bivariate data. So the first thing we want to talk about is what is a variable. And because when we talk about bivariate, the variate actually means variable. And bi meaning two. So for example, if you had a bicycle, test out my drawing, 2 wheels. Whereas the unicycle or univariate data only has the 1 wheel. Tricycle, 3 wheels. So a little bit of Latin to come back and help us out. So in terms of what this variable is, a variable is whatever you are measuring. So for example, if you are measuring the height of trees, the height, or how many meters, is your variable. If you're measuring the height of different types of trees, you would have height, so how many meters is one variable, and the type of tree would be your second variable. So let's have a look at this as a few examples to try and work this out. So we've got Ella measured the height and number of leaves of each plant in her laboratory. So Ella's not changing, so that's constant. She's measured the height and number of leaves. So the height of the plants will change. The number of leaves will be different for each plant, of each plant in her lab. So this is bivariate data. There are 2 things that she is measuring or recording. Rowan recorded the weight, so the weight is being recorded, of each of his cats. They're all his cats. We're not measuring anything about that, so that is constant. So this is, only has a single variable, so this is univariate, sorry, and this is bivariate, the first one. Our next one, Jaden observed the colour, so he's recording the colour and the model of each car in the parking lot. So there are 2 things he is recording, so we are still on bivariate data. Liam found the shoe size of each of his customers. So it's just Liam, it's just his customers. He's not recording anything else about them. If he recorded versus their weight or versus their height, there would be a second thing, but there is only one thing, which is a shoe size. So we have univariate data. Jordan wrote down the length of each song in his playlist. So we've got the length of the song. It's only one playlist, it's only Jordan, so it's only univariate data. Then Madison wrote down the genre, so she's recording genre and length of each song on her playlist. So the genre and length are 2 things being recorded, so we are on bivariate data. Now the important thing about bivariate data is we are looking for relationships between the data. So in this situation here where we've got genre and length, there may be a relationship between certain genres having longer songs or shorter songs. And this is where looking at your bivariate data can help you develop and make assumptions, and we're looking for a cause and effect. So for example, because it's a television theme song, it is more likely to be a shorter song. Or because it's a song from Meatloaf, I don't know, it's going to more likely be a longer song. So when we actually look at relationships, if we've got 2 continuous data sets, so where we're not recording colour, we're recording actual numbers, so it might be number of leaves versus height, we can then start to plot something on an x-axis and something on a y-axis. And then we can start to look at what are the actual relationships that we can see. So we can have what's called a linear relationship. So I don't know if you can read that one there, so I'll just write it out. You have relationships are linear. And for linear relationships, we're going to have, when we plot our x and y coordinates, so plotting something along our x and something along our y, we're going to get this something that looks a bit like it's going in a direction. It doesn't have to go through the origin. It doesn't have to go up. For example, a linear relationship could look like this, where it's coming down, it's not from the origin, it just depends. A non-linear relationship could look like this, and that's what we would call an exponential relationship. Another non-linear relationship, what could we have? We could have something that starts low and then goes up and then comes back down again. Now, the key thing here is there is a relationship in these. So there's a definite as whatever this x variable goes up, the y variable is also increasing, and then it comes down later on. The difference is when we're looking at something which is a relationship versus no relationship. So especially with our linear relationships, let's stick with that, we can have what's called a positive relationship and a negative. So a positive and negative, and this really refers to if we remember back what the gradient was of our line. So if our dots go up from left to right, we call that a positive relationship. If our dots go down, we call that a negative relationship. And we could even say, well, this is a positive linear relationship because it's forming a shape like a line, a straight line that is, and it goes up. So the next thing we look at is the correlation that we have between our data. So we can have a strong correlation and a weak correlation or no correlation. So I shouldn't be rubbing this out. So a fairly strong correlation means that the dots are very close together, and it very much almost, if you put enough points there, it'd form pretty much a line. If I was to say that there was no correlation, really we're looking at stuff where there's no pattern. And it doesn't have to have completely random all over the whole grid. I mean, we could have nothing down there, but there's still not really a correlation between this data. I couldn't say for sure as whatever's along here goes up, this one goes up as well. A weak correlation, we've got this bit of pattern, but there is still a bit of spread. So we can see, there's no high values on our y when the x is low. There's none down in this area. So it sort of seems to go up, but it's not very close together. So it's hard to sort of call that a strong relationship. And then our moderates, it's a little bit subjective, but it's just somewhere in between that. So we've got something that you might have one that's sitting out a bit and that's spread a bit more. It's not sort of this solid line that almost turns into a line on its own. So let's have a look at an example. So the scatter plot shown maps the height and weight of 9 people. We need to describe any correlations in terms of positive or negative. So we'll start with this in terms of positive or negative. So as our x-axis increases, our y-axis is also increasing. So as a general rule, this is moving up. So we have a positive relationship. Is it linear or non-linear? This, in general, it's forming fairly much a line as we go up. So I would be happy to say that that is linear. Is it strong, moderate, or weak, or none? That is, I can imagine a line probably going through about there, which most of the points sit on fairly well. So I would say it's relatively strong. So we need to determine what relationship, if any, exists between a person's height and weight. And this is where we start to use our describing words. So we could say a strong relationship, a strong positive linear relationship exists between height and weight, where, and this is our key comment, as weight increases, so does height. Or sorry, as weight, as got that mixed up, as height increases, so does weight. Now, in theory, we are talking about this like it is causative. So we're saying that weight is caused by height, and the reality is it's not always that simplistic. However, it's what we're trying to imply from our data. So let's have a look at another example. The Lifesaver Association wants to show that the number of lifesavers patrolling a beach affects the number of people who are saved each year. So we're using a table of data to create a scatter plot to determine any correlation between the number of lifesavers and the number of people saved that exists. So what we need to do, so we're actually going to go through and create a scatter plot. So we need to put something on our x-axis and put something on our y-axis. So we're going to put the number of lifesavers on the x-axis, and we're going to say the number of people saved on the y-axis. And we need to look at our data. This goes from 1 to, we'll say 10. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the number of people saved, that goes up to about 20. So I might go up in twos here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And so now it's just a matter of plotting out all of these points on our graph. So at 4 we have 12. So I'm going to put a line through that. 4, 12. 6 we have 18. 2 we have 6. 1 we have 4. 5 and 13. 8, 12, 4, 11, 3, 10, 6, 19, 5, 14, 3, and 9. Now before you ask, is there a difference between my X's and my dots? No, they should all be dots. So looking at this data, there actually appears to be a relatively strong linear relationship. There is one point here, it's at 8, oh, I've put the wrong number in, 8 and 22, that's why it looks out. But I mean, if you did have one outlier, I wouldn't be too stressed out about that. It's a single point, and anything that we're doing in terms of especially if it's biological, you're going to get outliers where there's systematic errors that occur. If you're using a ruler and measuring something, you would hope that you would always be quite close. So, okay, we have using the data to create the scatter plot. Describe the correlation in terms of positive and negative. So we have a positive correlation. As we increase the number of lifesavers, the number of people saved is also increasing. So we have positive, linear or non-linear. This fits a straight line quite well. So we would say linear. And is it strong, moderate, weak or none? Look, those points are fairly close together in terms of following a model. So I would be saying that that is fairly strong. So we need to determine if the number of lifesavers has an effect on the number of people saved each year. And I would say yes. The number of people saved is correlated with the number of lifesavers that are working. Now, could we really say that the number of people saved is dependent on the number of lifesavers? Maybe we have more lifesavers working at different times, but as a general speaking, we say, well, the idea is we're trying to prove that this is being caused by, so our y-axis is the change in our y-axis is being caused by our x-axis.